Hello everyone, and welcome to Chemistry 3120, Advanced Organic Chemistry. So today we're going to spend some time going over some conceptual concepts from second year organic chemistry. So let's get started. Okay, so from second year organic chemistry, there's many essential things that you'll need to use for this course. And these include key concepts such as things like acid-base chemistry, stereochemistry, reaction mechanisms, so on and so forth. So it may have been a bit of time since you've last taken organic chemistry. So let's definitely talk a little bit about some of the fundamentals from second year organic chemistry. So the first thing I'd like to touch upon is mechanisms, and the main type of mechanisms that you have seen from organic in second year. Okay, so if we have some type of molecule or ion like this iodine molecule, and if we treat this with CH3Cl, and we undergo some type of substitution reaction, the iodine acts as a nucleophile and the Cl departs as a leaving group. Your new product will be CH3I methyl iodide plus Cl minus. So this is a substitution reaction. It occurs in a concerted mechanism where the iodine attacks and at the same time simultaneously the chlorine leaves. So this is known as SN2 substitution, SN2. Another type of mechanism that you have seen before is if we take our same nucleophile and if we change our electrophile to something like this, we now have a tertiary carbon. This is our leaving group. However, what's going to happen first is that the chlorine group is going to leave first to now form what is known as a carbocation. This carbocation forms is because it is a tertiary carbocation. It's much more stable compared to a secondary or primary carbocation. And furthermore, the iodine as a nucleophile can't attack here. There is too much steric hindrance. So with tertiary carbon centers, you have to first have the leaving group leave. And then in a second step, you have your iodine attack this group here. So your product will be terbutyl iodide However, this mechanism is not SN2. It goes over two steps. It's unimolecular SN1. Okay, so those are the two common types of substitution reactions. Let's look at some elimination reactions that you have probably seen before. Okay, so if we have something like a hydroxide ion, and if we want to eliminate the bromine, in this orientation here, the OH minus can pick up this proton, form a double bond, and your bromine leaves as bromide, and your final product will be this, plus Br minus, and you'll have water also as a byproduct. So this is also known as E2, elimination. E2 elimination. So you've seen that before. And similarly, if we have a leaving group similar to the one we've drawn up here, and we want to undergo elimination, because it is a tertiary carbon whose substituent needs to leave, we cannot do direct elimination. This first needs to leave to form a carbocation, and then in a second step, the base will come, pick up that proton, and you'll form your double bond. So this will be your final product, plus your byproducts, Cl minus, plus water. So this is known as an E1 mechanism. Okay, so these are just some general review in terms of how these mechanisms work. Mechanisms are a language that rationalizes the outcome of a reaction, and it describes the movement of electrons. There are some very important rules with respect to how to draw and how to use these mechanistic arrows. So rule number 1. You want to draw the lone pairs at the site of the reaction. Number 2, always use the correct formal charge. So put in the formal charge. We will go over that in just a minute. You want to draw arrows from electron pairs or from bonds. Okay, you don't have positive charges moving from arrows. It's always electron pairs. And lastly, just to emphasize, arrows denote the motion of electrons. Okay, so one of the goals of this course, Advanced Organic Chemistry, is to have you think mechanistically in terms of how electrons would move in order for a particular reaction to occur. And one of the really neat things about organic chemistry is that all of the fundamental rules of organic chemistry, they all follow the same subset of rules. They all follow mechanistic rules. So if once you understand the flow of electrons, then you can apply that knowledge set to virtually any reaction. Let's go over formal charges. I mentioned that as rule number 2. Make sure you use the correct formal charge. So formal charge is used to assign a partial charge on an atom within a species. And there's a very simple or relatively straightforward rule that you can use to determine the formal charge. As you go and practice more mechanisms, you will immediately understand and recognize patterns and will know right away whether something is negative or positive. But at the beginning, I would use this rule in order to correctly assign formal charges. So rule number one, or the rule is that you want to use whatever atom your group number is in from the periodic table of that element and subtract the number of electrons in that circle. And I'll give you some examples. Okay, so if we look at a fairly straightforward example, and if we're asked you to draw or tell us what the formal charge is of this carbon here, well, you can probably tell me right away that it's 0. It's a neutrally charged carbon. There's no charge on that carbon whatsoever. Now, in terms of understanding and using the periodic table, I'm going to draw for you sort of a very shorthand periodic table that's very useful to know for this course, and it goes as follows. So we're going to have group 3, group 4, group 5, group 6, group 7. So here we have boron, carbon, nitrogen, oxygen, and then fluorine. And then underneath we have silicon, phosphorus, sulfur, and then we have chlorine, okay? So that's your group number for the element. So if you look at carbon, for example, that's group number 4. And how many electrons are in its circle? Well, each bond corresponds to 2 electrons. So 1, 2, 3, 4, that's 4 minus 4. That's equal to 0. So that's neutral. Okay, so that makes a lot of sense. Let's look at another example. What about something like carbon dioxide? So the Lewis dot structure of carbon dioxide looks like this. And if you were to ask, if you were wondering what the formal charge is of this oxygen, then we can use our handy formula and say, okay, what is the group number of oxygen? It's 6. How many electrons are in that circle? 1, 2, 3, 4 free electrons plus 5, 6. 2 electrons from each of those bonds. So the answer is 6 minus 6, 0. So that's a neutral atom charge there, CO2. Oxygen is neutrally charged. Okay, that makes a lot of sense. Last example here that I'll look at is this molecule here called dimethyl sulfoxide. And this exists in a particular resonance form in which I'll put electrons from this pi bond up to that oxygen. And then what I want you to do is I want you to determine the formal charge. Okay, so here's the neutral species in its Lewis dot structure. And we're drawing a resonance form. We've broken this bond, move electrons up to here, so now you have 1, 2, 3, 4, 5, 6, and like that. So let's ask 2 questions. What is the formal charge of this sulfur? Okay, so at this sulfur here, we are, if you look at your table here, you are in group number 6, okay? So your sulfur here also has a couple of electrons. And let's count the number of electrons within the circle. 1, 2, 3, 4, 5. 6 minus 5 is equal to 1. So the sulfur has a +1 charge. If you look at the oxygen here, the formal charge of this oxygen, it's group number 6 minus 1, 2, 3, 4, 5, 6, 7 equals -1. So therefore, this oxygen here must have a minus charge. Okay, so that's how you correctly assign formal charges. Okay, so let's go through an example of drawing a mechanism. So I'm going to find my trusted brush here and see what happens. Hopefully it doesn't smear too much. Not too bad, not too bad. All right. Okay, so let's go through an example mechanism. Let's look at the example of taking this molecule here, which is acetic anhydride. Actually, I'm going to draw it a little bit differently. I'm going to draw our alcohol, and I'm going to draw acetic anhydride over the arrow, and we're going to use some type of base here, which is called purity. So my question for you is, what is the mechanism for this reaction and how does it proceed? How does it function? How does it work? So here we have an alcohol, and remember we have lone pairs on the alcohol. This is a great nucleophile, and this is going to come and react with this acetic anhydride. And specifically, these carbonyl groups are very electrophilic. It's a symmetrical anhydride, so it doesn't matter which side it works on or which one it reacts on. So this is your electrophile. So it's seeking electrons, loves electrons, and this is your nucleophile. So in terms of drawing how this mechanism works, you're going to have your hydroxide group come in here, attack this electrophile, and then you're going to break the pi bond. The pi bond is a weaker bond to break. So you're going to form a tetrahedral intermediate. That's going to look like this. Okay, there's your new oxygen carbon bond. Oxygen here, because we have now extra electrons on there, is negative. And this oxygen here actually has 3 bonds. This one is positive. So you can apply those formal charge rules. Now, at this stage here, we have this proton that's attached to this oxygen that's positively charged. Oxygen is very electronegative. It's not very happy in this state. So it's very, very willing to lose this proton. And this is where you have your pyridine base that comes into play. This pyridine base is very willing to pick up that proton because this is very acidic and put the electrons onto the oxygen, making that neutral. Okay, now at this stage here, we still have our tetrahedral intermediate. So the electrons are going to come down, reform that initial pi bond that was broken, and then you're going to break this carbon-oxygen bond as I'm showing here. So if you do that, you are going to generate your alcohol that has now been transformed into an ester, and your byproduct will be this acetate anion. Okay, so this is what is known as base catalyzed acetylation of an alcohol. So that's one mechanism for this reaction. In fact, there's another widely respected mechanism for this reaction as well that I want to highlight. And the reason I'm bringing this now is that often with mechanisms, there's more than one way to describe how something works. So we're going to go through this mechanism again, but what has also been shown and hypothesized is that the pyridine can act as an organocatalyst, meaning that it can participate in the reaction, but because it's a catalyst, it's neither consumed or used during that reaction. So, how would that work? Okay, so we have the same ingredients. We have pyridine, and it's acting as an organocatalyst. So it must somehow be reacting with the electrophilic substrate. And again, using the mechanistic rules that we've gone over, pyridine has lone pairs here, and this is going to serve as the nucleophile to react at the site of acetic anhydride. So if we do this, we are going to end up with an intermediate that looks like this. Okay, so there's your tetrahedral intermediate, just drawing the rest of the molecule here. And here we have this pyridine attached. Now, what is the formal charge of that pyridine, or the nitrogen? The nitrogen has 4 bonds. If you actually apply that formal charge rule here, the nitrogen, you'll learn that the nitrogen has a positive charge, and that's actually really important. Now, at this stage here with our tetrahedral intermediate, we're going to reform the pi bond, and then this acetate group will leave. So what you have is this intermediate like this, and you have now an electrophilic center. Directly adjacent to it is this positively charged nitrogen. This overall here is a really good leaving group. So now when your alcohol comes and attacks, I'll redraw the alcohol down here. It's going to come, it's going to attack. Okay, you generate an intermediate like this. Now remember, this is very acidic, like we learned from before, and you have lots of pyridine around. So proton transfers, as you'll learn throughout this course, are the fastest type of chemistry that actually occurs. So before you blink, that proton's going to get removed. Here is your pyridine attached. And now we're going to collapse that tetrahedral intermediate. So this will come down, and then you'll release off pyridine. So your final product will still be that ester, as we had up there, the exact same product. And you can see here that pyridine acts as a catalyst and is recycled back. So this is also known as, base or like organocatalyzed. Organocatalyzed acetylation. So that's another way to draw that mechanism. But the most important thing I want you to understand is how we move those electrons and how we go from a nucleophile and how it attacks the electrophile. And while they do differ in their mechanism, they do get to the same eventual product. Okay, so I want to switch gears a little bit and talk to you about acid-base chemistry. Okay, so acid-base chemistry. So what is an acid? An acid is a molecule that's electron deficient, and it acts as an electron acceptor. Something known as a Bronson acid has a proton and acts as an electron acceptor. So something like HCl. A Lewis acid has a non-hydrogen atom, acts as an electron acceptor. So good examples, that would be something like aluminum trichloride or BF3. Okay, think back to some of those acids we had up there with the oxygen and the proton. That molecule was electron deficient. That's what made it so acidic. Okay, so I just wrote what I said. Okay, so this is the definition of an acid. Okay, they're all electron deficient molecules, and they're just, they're seeking an electron acceptor. So things like HCl or Lewis acids like BF3, AlCl3, for example. In contrast, a base is electron rich, and it's willing to donate its electrons to something that is deficient. And so a base is electron rich and donates its electrons. Okay, so a Bronsted base would donate electrons to a proton, for example, and a Lewis base would donate electrons to a non-hydrogen atom. Makes sense, right? So a Bronsted Okay, so for example, you've seen so many different bases before, something like sodium hydroxide, that's a Bronsted base, and then a Lewis base. And we'll look at lots of Lewis bases when we look at Lewis acid catalyzed reaction. Basically, the molecule that is willing to share the electrons acts as a Lewis base. Acid strength is measured as a function of pKa. So you've heard of the term pKa before. And pKa is a direct measurement of how strong the acid is. The lower the pKa, the stronger the acid, the higher the pKa, the weaker the acid. Okay, acid-base chemistry is really important in organic chemistry because during a lot of these reactions, it's very important for us to carefully decide which acid, which base to use, but more importantly, what is the acid's strength? How strong is that acid? How strong is that base? And we use numbers like pK to help us understand whether something is appropriate or not in solution. So I'll give you an example in terms of how we can determine the equilibrium side of a reaction using simple acid-base chemistry. So here's an example. If we take acetic acid and if we mix this with ammonia, there's going to be an acid-base reaction, fairly straightforward, right? The acid is from the acetic acid, and then the ammonia will pick up that proton. So that's your Bronsted base, Bronsted acid. So if you do this acid-base chemistry, you are now left with this reaction here. So this is known as your acid, or more specifically your Bronsted acid. That's your base, Bronsted base. This is also known as the conjugate base, and this is also known as the conjugate acid. So you've heard of those terms before. Now, we have two different acids here. We have acetic acid, or we have this ammonium ion here. Two different acids. And the equilibrium is going to lie on whichever side you have the weaker acid-base pair. So this is where pK values come into play. So the pK of acetic acid is around 5. Okay, maybe around 4, 5. Okay, so sort of mid to low single digits. The pK of an ammonium like this, a nitrogen with 4 bonds, is around 9 to 10. Okay, so which is the weaker acid? The ammonium is the weaker acid. Okay, so how do we determine what the Ka is for this type of reaction? How can acid-base chemistry help us with that? So, if we take a look here, and let's label this A1, acid 1, and if we label this A2, acid 2, and if we look at Ka, we can look at the concentration. That's going to be equal to the concentration of the products over the concentration of the starting materials. And this is going to be also equal to 10 to the power of the pKa of this acid on the weaker side, on this side, the right side, versus the pK of the acid on that side. So that's going to be equal to pKa acid 2 minus pKa 1, which is equal to pKa 10 minus 5. So that's going to be equal to 10 to the power of 5. Okay? So that means that this Ka here is equal to 10 to the 5, and the equilibrium is going to lie far to the right. So in fact, if we were to draw equilibrium arrows to highlight which side it goes on, the arrow going backwards is quite small. The one going this way is much larger. Okay? So it's always important to remember the weaker acid-base pair is where that equilibrium is going to lie. I have a good example that will highlight this acid-base chemistry in sort of an everyday, not everyday, but a scenario that you've definitely encountered if you've ever ordered French fries before. So, you might be wondering, what does French fries have to do with organic chemistry? Well, it's not so much the French fries that I want to highlight, it's this acid-base chemistry reaction that happens when you mix vinegar with salt to your French fries. Okay, so for example, let's say you order some French fries and you like vinegar. So you add vinegar to that. And vinegar is 5% acetic acid. And then you also add some sodium chloride because you like your French fries salty. So you add Cl minus, and then you say, well, wait a minute. I remember from this lecture that we have an acid. This is actually a potential base. Actually is a base. So if we do this acid-base chemistry, am I going to end up with CH3COO minus plus HCl? So if this is the acid, that's the base, this would be the conjugate base and the conjugate acid. And then you start thinking about this and you get a little worried because, you know, maybe your throat was hurting afterwards and you're thinking, well, am I really generating HCl on my French fries when I eat this? Because that would be very concerning. HCl is a very strong acid, as you know. You've probably used it in the laboratory. So HCl, let's look at the pK of HCl. HCl is a very strong acid. It has a pK of -7. And acetic acid has a pK of 5. So if you're wondering about whether you're going to be generating a lot of HCl, you can apply that same equilibrium reaction formula that we just applied over on that side. So that would mean that Ka is equal to the pKa, or 10 to the power pK2, which is that, minus pK1. So that would be 10 to the power of -7 minus 5. If you do that, that's going to be 10 to the power of -12. So if you think of the equilibrium of this reaction, that's a really small number. And what that tells you is that, in fact, the reaction is going back this way. And there's a tiny, tiny arrow going this way. So it's largely this way, where you have acetic acid as your predominant acid. This is the weaker acid-base pair compared to HCl. And that makes sense, right? If you're going to add acetic acid or vinegar to sodium chloride, you're not going to start making HCl gas, right? You're not going to start making HCl acid. That would be absurd, right? So you know it's safe to do this. So you can apply the same formula in thinking for any acid-base chemistry, and it's very important that you understand pKs because that directly influences what side of the reaction the acid-base chemistry will undergo. Okay, so in this case, equilibrium lies far to the left. All right, so I just want to highlight and give you some examples of some known pKs of some inorganic and some organic acids. And pK is something that you will learn more and more with time. You will learn that acetic acid has a pK of around 5. Ammonia has a pK of around 10. Water and alcohols have pKs of around 15 or 16. So at the beginning, it's beneficial if you can try to learn and understand and try to memorize these numbers. And the more you use them, the easier it will be to apply them. So here are some, I'll highlight some pK values. This brush is garbage. Some pK values of common acids. Okay, so these are inorganic acids. So we have HI, pretty strong acid, HBr, HCl we just talked about, sulfuric acid, H2SO4, H3O plus, the hydronium ion, phosphoric acid, H3PO4, hydrofluoric acid, H2CO3, HCN, hydrogen cyanide, ammonium, carbonate, water, H2, and then NH3. Okay, so HI, HBr, really strong acids. Okay, so these have pKs in the negative range, so that's the strongest one on this chart, minus 9.5. HBr is around minus 9. HCl we've looked at, that's strong, minus 7. Remember also that on the pK scale, it's based on a logarithmic scale. So for every unit in pKa, difference corresponds to a 10-fold difference. So here you can see that the difference between minus 7 and minus 9 is 2. So that's 10 to the power of 2. So there's a 100-fold difference in acidity between these two. H2SO4, minus 5. This H3O plus, around minus 1.7. Fairly acidic, right? We saw this type of scaffold with that base catalyzed reaction we saw earlier with pyridine, the alcohol, and acetic anhydride. H3PO4, now we're in the positive range, around 2.1. Hydrofluoric acid, you may have heard of hydrofluoric acid before. It's actually a very dangerous acid, but it's not so much dangerous because of its acidity. It's around 3.5, which is similar to around 5, which is the same as vinegar, albeit it depends on the dilution, of course. But hydrofluoric acid is dangerous because the fluoride anions that can penetrate your tissue, if you were to get some on you, can cause a lot of bone damage, and it's very toxic. It starts to form calcium fluoride deposits and essentially eats away at your bone. It eats away glass, so it's a very corrosive acid. You have to store hydrofluoric acid in plastic bottles, actually. You can't store them in glass because it will etch away at the glass. A little fun fact about HF. H2CO3. So if someone says, oh, HF is such a strong acid, you can correct them and say, actually, it's not that strong, but it's dangerous because F- does these nasty things. H2CO3, 6.4, hydrogen cyanide, 9.3. Ammonium, we just looked at before, that was around 10, so that's 9.4. Carbonate is around 10. Water and other alcohols are around 15 to 16. H2. So if this were to lose a proton, that would become H minus plus H plus. So it's not that favorable, actually. That's a very weak acid. So the pK of this is around 35. And similarly, NH3. For NH3 to lose a proton, it has to become NH2 minus. Again, that's not... You need a really strong base for that to happen. Those protons are not acidic whatsoever. And I just want to highlight the fact that NH3, which really does not have acidic protons, it's just far too high, and compare that to NH4, which has a pK of around 10. So these are relatively acidic enough. Okay, we'll be going through more examples of those later in the courses. Let's look at some pKs of some other acids. So we've looked at, of course, acetic acid a lot already today. But if we look at some derivatives of acetic acid, and what we're doing here is we're putting chlorine on this left carbon one at a time. The pK of this here is 5. As soon as you start putting a chlorine group on, replacing it with a hydrogen here, this is electronegative, so it's going to pull electron density away, meaning that the conjugate base, the negative that is placed here after the proton has left, is now a more stable molecule. So that means that this is going to be more acidic compared to that. So the value for this one is around 2.8. And if we add more chlorines here, you're going to increase the stability of that conjugate base, meaning that it's more acidic. And the pattern continues. If we look at this molecule here, which is an alcohol, by the way, and I told you already that alcohols in water have pK of around 15 or 16. This is called phenol. It's also an alcohol. However, when it becomes a conjugate base, you really want to ask yourself, how stable is that conjugate base? Well, you can see here that you can draw many different resonance structures, right? You can actually put the negative charge onto that carbon. Note that I'm using the resonance arrow here, or you can put the negative charge on this carbon. Or lastly, you can put the negative charge on this carbon. So, because you can delocalize the electrons so well, phenol has a pK that's much lower than 15 or 16. The pK is around 10, and that's because of that resonance effect. If you look at thiophenol, it's in the same group. I've erased my little periodic table that I had earlier. But the question again is going to be, well, what is the stability after it loses its proton to form the conjugate base? You can again form those contributing structures like I've shown here. I would encourage you to draw them on your own. But the sulfur atom is a bigger atom compared to oxygen. So because of its size, it can actually handle that negative charge better. And as a result, the pK is going to be lower because it's a more stable complex. So this one's going to be around 8. Okay? So it's not necessarily so much the numbers I expect you to remember, but understanding the trends of why something is more acidic compared to another similar molecule. Here's another example. Here's methanol. The pK of methanol is around 16. If you look at its thiolated derivative here, it drops down to 11. And again, there's no resonance because you can't move the electrons here. There's no double bond character whatsoever compared to this aromatic system that we just went through. But the sulfur here is much larger and can accommodate that negative charge to a much more significant degree. The last set of organic acids, I just want to mention their pKa's. Include this molecule here, and this ester here. Okay, so I've drawn acidic protons. Let's start with this one here, this ketone, acetone, and I've drawn in one of the protons here. So these alpha protons are acidic because a base can come and you can actually push electrons onto that carbon or put it up into this oxygen here. So the pK of this group here, it's not super acidic, but it's acidic enough for many interesting applications. So it's around 19 to 20. Okay, so we're looking at pK units here. And if you compare it to all the other ones we've looked at, it just gives you a little bit of context. This molecule here, in which you have acidic protons between two carbonyls, if you think of this mechanism here where you delocalize them up into the carbonyl, you can actually do this way, or you could delocalize it into that side. So because you have more area to which to move the electrons, the pK of this one's actually going to be much lower. It's going to be around 9, significantly lower if you have alpha protons that are between two carbonyls. And then last one for this lecture is this ester, in which you have an alpha proton. And yes, you can lose your proton just like we had done here, delocalized into the system. But this ester here has this oxygen here, and there's a lone pair of electrons on here. And those electron lone pairs are actually going to compete a little bit, or they're going to compete and make it harder for this acid to be removed, because the oxygen wants to donate in here and transfer electron density up to that group. So therefore, the pK of that acid is going to increase compared to this one. So this one is going to be around 24. Okay, so this is the review lecture and key concepts that are important from second year organic chemistry that will be extremely important moving on into this course. Okay, hope you enjoyed this first lecture, and see you next time.